Hi, I'm Cheon Hong, and I will briefly introduce our paper, AdaBM, on-the-fly adaptive bit mapping for image super resolution. Network quantization reduces the computational loads by mapping 32-bit floating point values of activation and weights to lower bit values. But one notable thing is that during test time, some images are easier to reconstruct than others. So adaptively assigning lower bits to such images, referred to as adaptive quantization, leads to a better trade-off. Especially for image super resolution tasks, adaptive quantization has proven effective. Although existing adaptive quantization methods provide better trade-off for inference, there are two remaining challenges. First, during training, finding the adaptive policy takes too long. For example, for a network of k layers and m bit width candidates, the network has to learn k times m policies, which in turn requires training with the full original training dataset for up to 40 to 70 hours. And second, during the inferencing through the adaptive modules, the k modules in this case, incurs non-negligible additional cost. On this basis, we find that layer-wise and image-wise adaptations can be processed separately. We observe that the image-wise variance of quantization error and the layer-wise quantization error are independent. This means that the layer-wise adaptation can be learned relatively among the layers, and image-wise adaptation can be learned relatively within the images. And what this does is that this approach simplifies the bit allocation into two policies, one for image-wise adaptation and another for layer-wise adaptation. This can dramatically reduce the search cost. And also, since on this basis, we find that layer-wise and image-wise adaptations can be processed separately. We observed that image-wise variance of quantization error and that of layer-wise are independent. This means that layer-wise adaptation can be learned relatively among the layers, and image-wise adaptation can be learned relatively within the images. What this does is that this approach simplifies the bit allocation into two policies, one for image-wise adaptation and one for layer-wise adaptation. This can dramatically reduce the search cost. Also, since layer-wise adaptation policy is invariant to the input image, it can be predetermined before test time, so only one adaptive model is processed during the inference. This is our overall framework. During the inference, an image is mapped to the image-wise bit adaptation factor based on its image complexity. Then, together with the layer-wise bit adaptation factor, predetermined based on the layer-wise sensitivities, the quantization bit width is adapted. I'll briefly go over each component. We use a mapping model to map an image to a bit width based on image complexity. Simply, if the complexity is larger than the upper threshold, the bit is adapted to increase. And these complexity thresholds are determined by collecting complexity measures of a small set of calibration images. Also, we use a mapping model that assigns the bit factor to each layer based on quantization sensitivity of each layer. Intuitively, the bit is increased for sensitive layers. The quantization sensitivity of each layer is estimated by calibrating the pre-trained model with the calibration images. The quantizer quantizes the input tensor given a bit width, upper and lower clipping range. And since bit width of quantizers are updated in our framework, the clipping range should also be updated. So, inspired by OMSC, we adjust the clipping ranges by minimizing the L2 loss with the unquantized tensor given the updated layer-wise bit width. Lastly, we noticed that calibrating the pre-trained model with the calibration images derives a decent initial point for the adaptive quantization network. Nevertheless, we fine-tune the mapping parameters with the calibration images to obtain a better bit mapping. The fine-tuning is done only with the LR images and without the ground truth HR image, using the reconstruction loss with the floating point model. And we also use a bit regularization loss. This process lets us find a bit mapping that achieves a better trade-off between accuracy and the complexity. These are some results. Compared to existing adaptive quantization methods, we achieve similar performance but with 2,000 times faster processing time. Also, compared to static quantization methods, we achieve a better trade-off, which proves the benefit of adaptive quantization. The visual results also show the effectiveness of our method. This is a visualization of when our method is applied to an 4K image in a patchwise manner. More bits are allocated for complex patches and also for sensitive layers. Lastly, we analyze the computational cost of our method. Not only is the processing time greatly reduced, but our method also reduces the inference cost compared to existing methods in terms of model size, bit ops, and latency. Thanks for listening, and feel free to reach me for further questions.